No. If they've got across the hall. And now we have this. Let me check with Jenny.
This here.
Oh, this is the drawer. Here we go. That's not it.
I've always thought that the lapel mic was a little dicey. Oh, what about...
Ah!
Sure.
Well, we're getting hooked up.
Should be pretty close. I can adjust the volume. Yes, it is.
It's a nice walk over. Hi, I'm Sue Chemnitzer. I worked at NSF for 45 years. Yes. Right. I was the engineering director, bioengineering and environmental. Thanks so much for I'm retired now. I think.
Good evening, everybody, and welcome. You're braving the cold temperatures outside, as they would say. No global warming here, right? I'm Dr. Scott Beard, Provost here at Shepherd University, and on behalf of President Mary J.C. Hendricks, I want to welcome you to tonight's very special event in the President's Lecture Series run by Shepherd's Office of Continuing Education and its director, Karen Rice. She does such a great job. And it's really an honor to introduce tonight's distinguished speaker. And I know Tom from my time in Washington, so I knew that I had to wear a bow tie tonight. Dr. Lovejoy is an innovative and extremely accomplished conservation biologist who coined the term biological diversity. Tom has so many amazing accomplishments in a career that has spanned higher education, research, foundation work, and service to several administrations. Currently, he serves as senior fellow at the United Nations Foundation, and in 2010, he was elected university professor in the Department of Environmental Science and Policy at George Mason University. He also served as president of the Heinz Center for Science, Economics, and the Environment from 2002 to 2008, and was the biodiversity chair of the center from 2008 to 2013. Before he assumed this position, Lovejoy was the World Bank's chief biodiversity advisor and lead specialist for environment for Latin America and the Caribbean, as well as senior advisor to the president of the United Nations Foundation. Spanning the political spectrum, Dr. Lovejoy has served on science and environmental councils under the Reagan, Bush, and Clinton administrations. At the core of these many influential positions are Lovejoy's seminal ideas, which have formed and strengthened the field of conservation biology. Following his initial use of the term biological diversity in 1980, he later gained international attention for the world's tropical rainforests, and in particular, the Brazilian Amazon, where he has worked since 1965. I think Camp 41 was the place we were talking about over dinner. In 1980, he produced the first projection of global extinctions for the Global 2000 report to the president. Lovejoy also developed the now ubiquitous Debt for Nature SWAT programs and led the minimum critical size of ecosystems projects. With 2 edited books in 1992 and 2005, he is credited with founding the field of climate change biology, a pioneer. He and co-author Lee Hanna are working on a new book on climate change and diversity for Yale University Press that will be out in January 2019. And if that weren't enough, Tom also founded the series Nature, the popular long-term series on public television. In 2001, he was awarded the prestigious Tyler Prize for Environmental Achievement, and in 2009 was the winner of the BBWA Foundation Frontiers of Knowledge Award in the Ecology and Conservation Biology category. That same year, he was also appointed a Conservation Fellow by National Geographic. Later, 2012, he was recognized by the Blue Planet with a prize, and in 2008 to 2013, he chaired the scientific and technical panel known as STAP for the Global Environment Facility, which provides funding to developing countries to meet their obligations related to the international environmental conventions. From 2013 to the present, he has also served as senior advisor to the chair of STAP. He is currently serving as science envoy for the Department of State. He holds degrees in biology from Yale University. So, ladies and gentlemen, please join me in welcoming our distinguished speaker and my friend, Dr. Thomas Lovejoy.
Well, thank you, Provost Beard and President Hendricks, and thank you all for coming out this evening to hear about the current overview of the topic of biodiversity and climate change. So let's just get right into it here. So that's biodiversity and climate change. That's a peregrine falcon looking down from a apartment building on Central Park West at the Climate Change March before the General Assembly in 2015. And this is the new book. Will be published on the 9th of January. And the first one that Scott referred to basically came out in 1992. And at that point, all you could really do is look at what happened to climate change in the past and imagine how that might play out in the future. By the time we did the second one in 2005, you could see the fingerprints of climate change on biodiversity wherever you looked in the planet. But it was such a fast developing field that 2005 was the year that scientists woke up to ocean acidification as a consequence of elevated CO2 in the atmosphere. So there's only one sentence about it in the second book, definitely corrected in the third. And you might ask, why have muskoxen on the cover? Well, part of the answer is muskoxen make it a profession not to be ignored. And so if there's going to be 20 books out on a table, that one is going to pop out. But the other part of it is that female muskoxen browse in the winter through the snow to get enough food to produce calves. And now, more often than not, instead of brushing away snow, they encounter frozen rain, and they're raising underweight calves. So that's the kind of biological detail that plays out wherever you're looking at this topic at biodiversity around the planet. So in 1896, this very famous, very important Swedish physical scientist, chemist, Svante Arrhenius, asked a really important question. And that question is, why is the planet a habitable temperature for humans and other forms of life? Why isn't it too cold? And the answer was the greenhouse effect. And it was that very famous paper in 1896 on which all climate change is based. And it's the greenhouse effect and the presence of CO2 at natural levels in the atmosphere. And he literally calculated with pencil and paper what doubling pre-industrial levels would do to the Earth's average temperature. And it came out exactly where the big, fancy supercomputer models put it today. So the science behind climate change actually is really very old and is essentially unquestioned. What Arrhenius would not have been aware of course, is a lot about the previous history of the climate in the last couple 100,000 years. And in particular, that last 10,000 years on the right, a period of unusual stability in the climate of the planet. And that 10,000 years includes all recorded human history, a significant portion of unrecorded human history, the origins of agriculture, the origin of human settlements. Basically, the point is the entire human enterprise is based on the assumption of a stable climate, and therefore it makes very little sense to be disturbing that. And in that same 10,000 years, of course, all ecosystems adjusted to a stable climate. And that, of course, is now changing, and we're seeing lots of signals about that in nature, some built around the solid and liquid phases of water. So lakes freezing later in the autumn and ice breaking up earlier in the spring. I think we're all acutely aware of essentially the thinning and the retreat of the sea ice on the Arctic Ocean. This graph will only take it to 2007, but it has basically continued beyond the point that you see here in the same direction. And glaciers are in retreat in almost any place you look in the world. So here we're looking at Glacier National Park, well on its way to being that only in name. And in the tropics, where there are glaciers on tops of very high mountains like Kinabalu in Borneo or Kilimanjaro in East Africa, all tropical glaciers are retreating at a rate that they will be gone within 15 years. We're also seeing definite increase in sea level. This is actually a pretty old graph. Just shows a little bit of that sea level rise up to 2000. And it's gone beyond the initial rise, which was mostly about the thermal expansion of water, to include the addition of considerable melt of ice that is land-based. Ice that's on the ocean, like in the Arctic Ocean, it's basically like an ice cube in a glass, so when it melts, sea level doesn't rise. But when it's ice coming off of Greenland or at Antarctica as meltwater, it contributes seriously to sea level rise. On the eastern shore, there is a wildlife refuge, the Blackwater National Wildlife Refuge. And through a combination of natural subsidence of the land, an ongoing process sort of in reaction to the retreat of the glaciers, but also together with sea level rise, you can see that this refuge is well on its way to becoming a marine refuge. And there is definitely a probable increased frequency of more intense tropical cyclones. When I used to talk about this, I couldn't be quite so categorical about it. But every year we're seeing the evidence get stronger and stronger. And there is absolutely no question about the increase of wildfire in the American West. We've just been through another big fire event out in California. And basically a lot of this is driven by warmer summers and earlier snow melts and less snowpack. So it's just basically drier in those forests, as well as some other things happening to them I'll touch on later. So the rest of this talk is going to be about how biology is responding to climate change. And one of the first things that gets noticed, whether it's at Walden Pond or here at the Royal Botanic Gardens at Kew, is that different species of plants are blooming earlier than in the past. And it's not just plants that are changing their annual timing, it's also animals that are changing their timing. And so tree swallows are migrating earlier, nesting earlier, laying eggs earlier, and there are even a couple species of birds in North America which have ceased to migrate. More interesting in a way, some species are changing where they actually occur geographically. So this is one of the two best-known species of butterflies in North America, the other being the monarch. And the Edith Checkerspot has clearly been moving northward and upward in altitude in response to climate change, tracking its required climatic conditions. And Joshua trees are now actually growing outside of Joshua Tree National Park. So this begins to create some problems for how you design and manage national parks. And the National Arbor Day Foundation, which is hardly some wild-eyed environmental terrorist extremist organization, but it's just, about people who like to plant trees, literally found it necessary to produce a new hardiness zone map to guide its members as to which species they could be successful at planting and raising where they live. We're also seeing lots of changes in the oceans as well. Fish species are changing in distribution, plankton species changing in distribution. If anything, those kinds of changes seem to be happening faster in the oceans. Lobstering is dead in Long Island Sound, and it's literally moving north, so they're beginning to worry about that in Maine. And when you look at the Chesapeake Bay, the great estuary on the east side of North America, where these eelgrass communities are hugely important for blue crabs and various other kinds of seafood, it turns out the eelgrass communities are very temperature sensitive. They will not grow and thrive above a certain particular temperature. I don't have it in my head. But as a consequence, essentially the southern limit of eelgrass communities is moving northward year after year. And even in places that are far from the poles, far from the boreal region, far from the temperate region, places like the Monteverde cloud forest in Costa Rica, you can see the fingerprints of climate change. And these forests are quite extraordinary. They basically depend for 98% on their moisture on condensation from clouds. And what is happening in Monteverde is clouds are now beginning to form more frequently at higher altitudes and less at the customary altitudes. And that's a really serious consequence for an ecosystem that depends so heavily on cloud condensation as a source of moisture. We're also seeing a whole lot of events which those of us in the field call decoupling events, where you have two species or two features in nature closely timed, but it turns out that one of them has used the cue of day length to determine the time to change, and the other has been using temperature. And so an example here is the snowshoe hare, which depends on day length, whereas the habitat that basically it has that white winter fur to be camouflage for it is instead of being day length dependent, it's temperature dependent. So you're getting increasing observations of snowshoe hares in brilliant white pelage standing out, perfect targets for predators in no longer white landscapes. So this slide, which I would penalize any of my students for if they produced it, because it is basically illegible, right? That's on the screen to make the point that what I've been telling you is no longer just the individual anecdote. There's no question that you can see the imprint of climate change on the biodiversity and biology of the planet, and that it is statistically robust. So what I was just telling you about is, pretty minor ripples in the fabric of life. So the real question is, what does it look like looking ahead? And then ultimately, having decided that maybe it doesn't look so good, what can we do about it? So there is a solution at the end of this talk. So don't get discouraged. So one of the things that scientists concerned with this topic can do is basically describe the climatic envelope of a species or of an ecosystem. In this case, the sugar maple forests of New England and southern Canada. And just figure out what are the conditions under which they grow. And then you can look at future climate models and figure out where those conditions will exist. And if you do that for sugar maple, the bad news is that all of the 5 major computer models for climate show that you will, at double pre-industrial levels of CO2, anything you like sugar maple for, whether it's autumn foliage or maple syrup or maple sugar, you're going to have to go to Canada. This I put on the screen to make 2 pretty simple-minded but often overlooked points. The first is that for terrestrial organisms, the 2 most important physical factors are moisture and temperature. For aquatic organisms, it's temperature and pH or acidity. And all of those are changing. So we anticipate that it will be really very challenging for cold water, freshwater species like trout. Basically, it will be very hard for them to track their conditions beyond a certain point. We also know that species which live at high altitudes, like this charming rabbit relative, the pika, which lives in isolated colonies in the Rocky Mountains. Basically, the high altitude species will move up in response to climate change, tracking their conditions, until there is no further up to go. So at least one of those colonies of pikas has already winked out. And obviously there are going to be serious challenges for coastal species with sea level rise. We'll talk a little bit more about that later. Some will do better with it, and others not so well. This is one that's been in the news a lot in the last few months, the salt marsh sparrow, which basically nests between 2 major high tides in the spring. And it's really getting squeezed in terms of the vegetation available for it to do that, because the vegetation is not changing as fast as the sea level itself. So if you look at Everglades National Park, which clearly will have a sea level issue, with 84% of the park less than 1 meter in altitude, saltwater intrusion is going to be a big issue, and that will affect a whole variety of living things. And there will be a lot of change in terms of the coastal vegetation, a lot of dieback in the mangroves as they march inland, just because mangroves can only grow in relatively modest depths of water. And we expect that something like the American alligator is actually going to suffer competitively with the American crocodile because it is much more salt sensitive. The crocodile can actually excrete salt, so it's likely to do better going forward. And anything on islands, obviously, are extremely vulnerable, especially low-lying islands. So the key deer obviously will only make it if they're taken somewhere else. But even islands that have a fair amount of altitude are going to have a lot of species challenged by climate change, because basically the climate on the entire island is going to be changing, and there will be limited opportunities for a lot of those species to track the conditions they need. And of course, there are all the ice-related species, of which the polar bear, of course, is the poster child, species which depend on ice as part of their natural history, and they will be seriously challenged. So, looking ahead, there's some serious complications, and I'll go through these one by one. The first of these is that we know glaciers came and departed in the past, and we know that most of the biological diversity made it through those glacial swings. But the big difference today is what we've done to our landscapes. So most of our landscapes have been highly fragmented by human activities. As here in this county in Wisconsin, you look at the forest cover in 1831 on the upper left to 1950 on the lower right, the consequence is that we've created basically an obstacle course for plant and animal species as they endeavor to track their required conditions. That, of course, is something we can do something about. We can put natural connections back into the landscape. Restoring riparian vegetation goes a long way to doing that, for example. But the next complication is much more challenging. And basically, we know that entire ecosystems don't move in response to climate change. It's the individual species that move, each in their own direction and at their own rate. And so basically, at a certain point, we have all those species moving not in any choreographed or orchestra-like way, and the ecosystems basically are coming apart. And the surviving species then reassemble into something which is hard to even imagine in advance. So here we're looking at this as it actually happened after the retreat of the last glacier in Europe. And we're looking at, I recall, 2 tree species, 3 mammal species, and an insect species. And you can see there's no common pattern amongst all of those. So the conclusion I draw from that is that's something to be avoided, because it begins to be very hard to manage biologically. We also know that even though the computer models are linear and gradual, that the climate system itself is not linear or gradual. So we can expect some abrupt changes at some point. Maybe it will involve what's called the global conveyor belt, which basically brings warm water from the Pacific and the Indian Ocean back around up through the Atlantic, where it sinks between Greenland and Europe and doubles under itself and returns. That has actually been known to shut down in geologic time. Are we close to that? Nobody really knows. But since we're talking about biology here, we're already seeing abrupt changes in ecosystems. And one of the best examples is what's happening to coniferous forests in western North America, all the way from southern Alaska to southern Colorado. And basically what is happening is the warming climate has tipped the balance between the coniferous trees and the native bark beetles. So here we're looking at pine beetle outbreaks from 1959 on, and in the beginning you can barely see the little red specks, which are the outbreaks. But as time goes on and the summers are longer and the beetles get in an extra generation and more survive the winter, the outbreaks get more and more serious. And you'll see when we hit 1985, which was a severe cold winter, they get knocked back, but nothing like they got knocked back before. So part of the fire problem in California that we've just been through is because there are a lot of standing dead trees. And so this is a really serious problem, and nobody really knows where it's all headed and what those forests will turn into. We're also seeing abrupt change in marine systems, and in particular in tropical coral reefs, which all look like this when I was a graduate student. These wonderful, technicolor, highly diverse, highly productive, fascinating ecological systems within 100 meters of which 5% of humanity lives and depends. And it turns out that the very fundamental partnership on which the tropical coral reef system is built, namely between the coral animal and an alga, breaks down after exposure to not a lot of increased temperature for not very long, and the coral animal basically ejects the alga, and basically the whole system collapses and you get what are called bleaching events. And last year, 60% of the Great Barrier Reef bleached. Now, can coral reefs come back from bleaching events? Yes, but not if it gets to be chronic. Are there things we might be able to do to sort of basically midwife them through some of these events? Probably, but it's pretty labor intensive. So one of the points I'm trying to build up here is that you can do all the fancy computer modeling of climate to a fairly well. You can do the similar modeling for vegetation, and it's never going to tell you about things like the coniferous forests or the tropical coral reefs, because that comes down to the idiosyncratic biology of just, in some instances, just a couple species. And so we're also seeing, I think, even bigger scale change, which I call system change. And here we're looking at one of my favorite images, which is how moisture is generated and moves around the world hour by hour. I won't take you through 365 days of this. But you see that most of it is generated over the oceans and over the equator, with one really interesting exception. namely the Amazon basin, where the moisture comes off the tropical Atlantic and enters the Amazon basin, the world's largest rainforest, and it recycles as it moves across the basin because it is forest. So that system looks like it is flickering at the moment. There have been serious droughts in 2010, 2005, again in 2016. My colleague Carlos Nobre in Brazil and I believe that it's flickering and sending a signal that it's close to Amazon dieback, in which that recycling would break down and you would literally get insufficient rainfall in the southern and eastern Amazon to actually have a rainforest. You'd get savanna instead. And of course, were that to happen, there would be a lot of biodiversity in peril. The livelihood of the indigenous peoples of that part of the world would be seriously undermined. And on top of that, there would be a great pulse of carbon from dying forests going into the atmosphere. I mentioned earlier ocean acidification. Well, that's a major system change. And basically, the oceans are now, it's not going to sound like much, 1/10 of a pH unit more acid than in pre-industrial times. But that's actually a logarithmic scale, so that's 30% more acid. And why do we worry about 70% of the Earth's surface changing chemically? Among other things, it's because there are tens of thousands of species that depend on the carbonate equilibrium in the oceans to build their shells or their skeletons. And that is very pH dependent. So the more acidic it gets, the harder it is for them to marshal the carbon. And we know about some of these organisms. We know about corals, we know about giant clams. But then there are important ones we don't know much about. Few people know about this marvelous creature called the sea butterfly. And I'll show you it in motion in a second. But basically, this is not a tiny snail, a teeny snail, which instead of moving along on its foot like snails usually do, the foot has been modified so they are sort of like flapping wings. And basically, sea butterflies use them to stay up in the water column. And they exist in just incredible numbers at the bottom of the food chain in the North Atlantic and off of Alaska. And they are very sensitive to ocean acidification. So I've been trying to build a picture here that we're getting into a danger zone in terms of the scale of the changes we're affecting the Earth system, that it really doesn't make sense to be playing at that kind of scale. And led me some time ago to decide that that 2 degrees as a target to limit climate change actually was too high from a biological perspective. And there are a whole bunch of reasons around what it means in terms of ice systems. But major ecosystem disruption and the ability to manage the planet biologically is a very important reason to be concerned about that. And if you want to just take one little fact away to remember that with, the last time the oceans were 2 degrees, the planet was 2 degrees warmer, the oceans were 4 to 6 meters higher. And that's all you need to know, right? Just think what that means for any coastal state, for example, small island nation states, big countries like Brazil, which are so pleased with their beaches, and the rest. So the question then becomes is what should we be aiming for? And Jim Hansen was the first to say we ought to try and aim towards something like 350 parts per million of CO2 in the atmosphere, which compares to 280 as the natural level. We're currently at about 400. And that has been beginning to take on, and quite recently there's been a fair amount of international agreement that we should try and stop at 1.5 degrees. So this is Dr. Planet. He's made the diagnosis. What is he going to prescribe? Well, there are a bunch of things you can do around conservation strategies. There are a bunch of things to do about limiting greenhouse gas concentrations, including lowering them in the atmosphere. So mitigation is the term for the reduction of greenhouse gas emissions, but it actually could refer to lowering them as well. And then adaptation is just the sensible thing. What are you going to do to cope with the effects that are already happening? So on conservation strategies, there's the obvious one of improving natural connections. Another really obvious one to essentially minimize other things which are affecting these ecosystems, to avoid negative synergies. And there are particular places where you can begin to imagine how you might do it, at least in the beginning of sea level rise and climate change. And one of them is just restoring the natural sheet flow of water in the Everglades to the extent you can do it today will actually build up resilience against coastal storm surge. There obviously is a gigantic energy agenda. I don't pretend to be an expert on that. But then there's a piece that people usually don't pay much attention to, and that is how much CO2 is going into the atmosphere from deforestation. And in fact, take it a little more broadly, how much is going into the atmosphere or has gone into the atmosphere from what we've done to living ecosystems. And it turns out the numbers are bigger than we thought, which is discouraging in one sense, but encouraging in the other, that it's possible to restore those ecosystems, get some of the benefits you would want anyway, but also pull CO2 back out of the atmosphere. So this is the equation that we have to deal with on a, well, it doesn't want to move. That's weird. Here we are. So this is essentially the annual equation that goes on, about 20% coming from destroying forests and other ecosystems, about 5 times as much from burning old ecosystems, which is what fossil fuels are. And then half goes into the atmosphere, and the other half is more or less evenly divided between the land and the oceans. And because greenhouse gases stay in the atmosphere for a long time, if we can play with that equation, and maybe even reverse one of those arrows, we could actually avoid some very damaging climate change. So, the really interesting new figures as of the first week of January 2018 is that the estimate of the CO2 in the atmosphere from destroyed and degraded ecosystems is twice as much as science understood it to be before. And that means there's twice as much that could be pulled back out of the atmosphere through ecosystem restoration. And interestingly enough, the planet's done it before. There are twice in the history of life on Earth, there have been just unbelievably high levels of CO2 brought down to pre-industrial levels by natural processes. And the first time was when plants emerged on land and began to photosynthesize like crazy. The second time was when modern flowering plants were doing it. So that's very encouraging, but we don't have tens of millions of years to wait for that to happen. So this is the new numbers, 450 to 500 billion tons of carbon up there in the atmosphere from destroying and degrading natural ecosystems. And so the idea that's beginning to get a little attention and take some root is if we actually got ambitious about restoring ecosystems, which would include forests, of course, because they're very forest dense, but not just forests, but other kinds of ecosystems like grasslands and grazing lands. When you restore those kinds of ecosystems, they start storing a lot of carbon underground. You actually look at a prairie soil, the carbon storage goes down for like 12 feet. And it was all down there until John Deere invented his plow, right? And there's no reason a lot of that can't go back. And so when you start restoring these ecosystems, you get the benefits of greater productivity, more grazing if that's what you wanted to do. And one piece of it will be looking at agroecosystems and designing ways to actually do agriculture in ways that accumulate carbon in the soil, not leak it. And when you accumulate carbon in the soil, surprise, you get increased soil fertility. And there's a whole additional piece of this that wasn't particularly apparent when we were first looking at all of this. It's what you can do with what's called blue carbon. So that involves all kinds of coastal wetlands. And primary amongst all of those, of course, are mangroves, which have a tremendous amount of carbon, not only in the living plants, but in the sediments beneath them. That's a really washed out slide to show where mangroves occur. And I thought I'd share with you this really interesting economic analysis of shrimp farming in Thailand, which is always done there by ripping down the mangroves to create ponds to raise the shrimp. So if you look at it in conventional economics, well, you get a pretty nice return. Why wouldn't I do that? But then if you look a little more closely and remove the subsidies, it's beginning to be a marginal call. And then if you look at the actual public services of mangroves in terms of nurseries for fisheries, you would never dream of doing that to mangroves at all. If you want to do shrimp farming, put them somewhere else, but don't rip down the mangroves. So this will give you some sense of the power of ecosystem restoration. Here we're looking at soil carbon debt. This is representing how much carbon has been lost from soil. So a lot in Europe and UK and parts of the upper Midwest, China, etc. And now we're going to see above ground carbon storage as it is essentially right now. This is 2016. So you can see there's a lot of carbon stored in the Amazon and in the Congo and some parts of Indonesia. This is the potential carbon storage if we did a lot of that ecosystem restoration. And if you did all of that, that's what carbon storage would look like above ground. These last slides I've been showing you have been produced by the Woods Hole Research Center. You see their logo there. They haven't even been published yet, but I was able to persuade them to let me include them in this talk. So they will be out pretty soon, and I think will bring to life this whole notion of ecosystem restoration. Of course, we're not talking about reforesting Manhattan or the Ile de la Cité, but there is an amazing amount of degraded land on this planet that could be brought back to productivity and give us a carbon value as well. So this sort of lays it all out, essentially side to side. And then there's the big challenge. You know, there are going to be another couple billion more people expected on this planet. And they're going to have an adequate diet. They're going to have an adequate quality of life. So we need to start thinking some more about what we define as the adequate quality of life. Maybe it's not getting a new iPhone every 6 months. But more important, a couple really good scientists have looked at this challenge of how do you feed that number of additional people and figured out you can actually do it without destroying another square inch of nature through a combination of improving productivity judiciously in places that can use it, reducing food waste, which is like 40% of all food is wasted. In this country, it's more often than not the stuff that we accumulate for too long in our refrigerator. And then after it becomes an experiment, you know, your spouse tells you to get rid of it. And then the third part of it is just changing our diet. And our doctors have been telling us to do it anyway. So in a broad brush kind of way, all of this is doable. The issue is how do you put more order into the development process and more awareness into people about their individual impact. But in the end, the point is that this is a living planet. It's a linked physical and biological system. We manage it that way, which means managing ourselves, of course. We literally can regreen the Emerald Planet and ensure that it is habitable for humans and other forms of life. Thank you very much. Please.
What advice do you have for the students in the
I'm cutting in and out. What advice do you have for the students in the audience
So,
study climate science in the future and help us all?
So I would say two things. One is learn enough about this so that you're knowledgeable, but you don't have to become a PhD or anything to do that. And then the other thing is to realize that every individual can make a huge difference. Everybody can plant a tree. Everybody can talk to somebody else. There is an awful lot we can do individually and together. Yes?
One of your slides talked about non-biological carbon removal. And I was just wondering, years ago they were talking about trying to develop a artificial photosynthesis process. Have you heard of it? Has there been any progress in that arena or some other way? You know, there's sequestration, you know, at the coal plants and stuff, but is there some other way that could be developed to, beyond just planting more trees and stuff, to suck carbon out of the atmosphere?
I'm very glad you picked up on that point. So I was trying to keep this talk from going too long, and I skipped over it. That point was there because as marvelous as the potential of ecosystem restoration is in this picture, especially compared to what we understood a year ago, it's not enough. So we need to get really smart about other ways to pull CO2 out of the atmosphere, as well as convert very quickly to non-fossil fuel sources of energy. And, you know, I know little bits and pieces of stuff, nothing that's a categorically, you know, detailed answer. But there are really interesting things, like you can actually make a high reflectance, high albedo concrete using seawater in chimneys full of CO2. It's pretty expensive, but if Washington, D.C. repaved its streets with that high albedo concrete, they'd actually make money, because it would lower the average temperature of the city about 2 or 3 degrees annually. So there are possibilities out there that I think would surprise people. And, you know, I'm on the board of something at University of Michigan called CO2 Sciences, which is looking for just these kinds of things which will find value in CO2 by turning it into something inert. And then hopefully the market will take it and run with it. Yes, sir. Yeah, you've got to be recorded for posterity.
So as a young person, I, am concerned because obviously I'm going to be here for a while. And, recently politics has played a big part in climate. Climate politics has really been changing a lot. And, in Brazil, which owns a very large majority of the Amazon rainforest, they recently elected a president, Bolsonaro, who says that he does not care what happens to the Amazon rainforest. He would be totally open to completely deforesting it in order to get as many resources out of it as he can. A lot of people in Washington right now would tend to deny a lot of the science that goes into climate change and things like that. And so as a young person, I'm growing concerned, seeing all of this. And I just wonder if you actually think that climate politics are changing for the better or for the worse in general.
Well, if I looked at it right now, particularly because I, do a lot with Brazil, as well as, my office is 2 blocks from the White House when I'm downtown, right? It's not a pretty picture. But even without a national commitment on climate change, it looks pretty certain that the U.S. actually will make the commitments it made in Paris. Now, were those sufficiently ambitious? No. But those were at least the national commitments we made. So a combination of what's going on at the state level and the urban level and the corporate level is actually driving that. And that's the kind of stuff you don't see in the headlines or, see in Twitter and stuff like that. The Brazilian situation I'm working on really hard. Bolsonaro was elected primarily because the public were disgusted with corruption and street crime and the state of the economy. And his appointments for Minister of Justice and Minister of the Economy are actually excellent. And they actually care about these kinds of things. Now, how much will they speak up? I don't know. But I'm working on it every day, right? And I'm not alone, of course. So, I mean, I don't think let me turn it around another way. So Bolsonaro may do some really stupid things. And the risk of his tipping the Amazon into dieback is a real risk. But, you know, this will surprise you, but Brazil is the country which has the greatest percentage recognition of the word biodiversity of any country in the world. Public opinion about the Amazon is very positive. The media are extremely, you know, environmentally oriented. So there are a lot of pieces like that that don't change overnight when somebody gets into office and starts shooting his or her mouth off. So just you know, it will depend on you not giving up, right? Yes?
So I'm thinking about the IPCC report that was released very recently that basically told us our time frame to get our act together is quite short. So I was wondering, is it possible to restore these ecosystems in time before the climate changes so much? And if it can the climate reach a point to where these systems cannot be restored?
Well, that's a really good question. So that's all about scale and rate. And if you would look at current trajectories, you know, you would go to the nearest bar and never reemerge, right? But you know, things do change. And particularly, you know, when the younger generation starts speaking up, because let me tell you, parents hate to look stupid in front of their children. Right? I mean, it's the voice of young people is very powerful. And as you were saying, you know, I mean, you're going to be here in the year 2100, and so you have a big stake in this. So don't let anybody, you know, tell you can't make a difference, because you really can.
I was wondering if, when you say to restore the environment, I mean, is the goal to restore it to what it was historically, or is the goal to engineer it so that it is more efficient at absorbing, like, CO2?
So basically, ecosystems are pretty efficient at doing that in their natural conditions, and they're very, very complex systems. So one of the first reactions some people have, we should plant a lot of fast-growing eucalyptus trees. Yeah, cut down the whole Amazon, bury it, and then plant a whole bunch of eucalyptus trees. Well, ecosystems don't work very well that way, and they would all come to maturity at the same time, and it would be a real mess. You're much better off using the incredible complexity and diversity of nature to achieve those aims.
Might you have any comment on the plans in West Virginia and Kentucky? There's a big strip here where they're talking about building a horrible strip of natural gas and related facilities that compare to what I understand in the New Orleans area that has become known as Cancer Alley. And I understand you don't have to go to Washington to find some nutty politicians. You can find a lot of them in this area. And almost everyone, I understand, is supporting this huge natural gas field. It's like lemmings going off the, I don't know. Can you comment on that?
So I don't know a lot about that particular example that you cite, but I would make a general statement that while natural gas, of course, is a lot better than any other fossil fuel, it's still a fossil fuel. And so we really need to hasten our transition to a different energy base. And once that starts to happen, a lot of the corporations that are driving all of that are suddenly going to find themselves with stranded assets on their balance sheets. You know, and
Oh, you think that is going to happen?
Yes, it's going to
I
happen.
hope so.
No, it's going to happen. It's going to happen because they won't be able to sell it, right? So I think we may not be that far from a major sort of tipping point in all that kind of behavior.
I'm concerned if we get too many pipelines in here, it's just going to get harder and harder to.
Well, you're right. So
turn to
anytime you put in
renewable energy.
anytime you put in some kind of installation, the tendency is to let's use it till it's economically exhausted, right? Because we put all that money in. So it's an issue, no question about it.
Am I understanding you right? That what you are saying in all of this is that each and every one of us have to look within ourselves and make some decisions on how we live each day? Am I getting that from you?
That's part of it, definitely.
That you know, and I work at Burger King, which you know, because I'm in a uniform, I had to come from work. I watch, okay, but what I watch is I watch a lot of food being thrown away. I watch people not caring. So, like, if we make that decision on a personal thing of what we can change in our life by simply maybe not have a triple Whopper, just have a Whopper. Okay, I mean, you know, I mean, honest. I mean, I'm just trying to say. I mean, because that, you know, if we actually make a personal commitment to ourselves of what we can do for this earth, that's a ripple effect. And so, am I understanding that from you?
I completely applaud and encourage that, and especially for the younger members of the audience. So I grew up in a pretty privileged background in the middle of Manhattan. But my parents had gone through the experience of Second World War and rationing, and the experience of the Depression. And they had, as a consequence, a natural frugality in how they looked at things. And sort of the quintessential example was, you know, aluminum foil appears. Oh my goodness, this wonderful new thing for the kitchen. But what did they do? They used it and washed it and used it and washed it until finally it fell apart. It's not so hard to start thinking about some basic frugality again. And you can do a lot of that without changing a lot of your quality of life. Whereas letting what we've just been talking about happen is going to change the quality of life. So, great.
Thank you all for coming. We have a lovely reception out in the